Hi, everyone, and welcome to this edition of the Humans of AI podcast, where we're going to be focusing on the humans behind the algorithms. My name is Paul Cunningham. I'm a director at the Data Science and AI Association of Australia and the founder of the Sydney Machine Learning Meetup, the largest machine learning meetup here in Sydney, Australia. So for this edition of Humans of AI, I was lucky enough to interview Professor Maurice Pagnucco, who is one of the busiest people I've met in this space here in Sydney. And that's because he fills two very important roles at the University of New South Wales, also commonly known as UNSW. So Professor Maurice Pagnucco is the Deputy Dean of Education, so that in itself is a huge role. And he's also the head of the School of Computer Science and Engineering at UNSW as well. Okay, so two massive roles and an extremely busy man. I was lucky enough to have a little bit of time with him to essentially go over the history of machine learning, but essentially with his take on it. And all his involvement in various fields of machine learning, but we'll get to that in a bit. So Professor Maurice Pagnucco, his expertise is artificial intelligence, reasoning, robotics, knowledge representation, belief revision, and reasoning about action and change. Also, as a precursor to this edition, I'd like to point out that this was actually the very first podcast that I ever recorded for the Humans of AI. It's only coming out now because this is the podcast that required the most editing, as I was quite nervous for this one. So with that being said, I'd really like to, get started with the podcast, and I really hope you enjoy it. Cheers. All right. So, the first thing I'd like to ask you is, can you tell us a little bit about your history in the field of artificial intelligence? And I guess the crux of this question is, what drew you to the field in the first place?
Yeah, that's a good question. So I started off in my undergrad years as a mechanical engineer. And at the time I was studying a degree program, which was essentially like a dual degree. So you did the first 2 years of mechanical engineering, you transferred to science and did your science degree. And then you transferred back to engineering and completed the engineering degree, except that I didn't transfer back. So as I was studying mechanical engineering, I had to do a computer science course. And I had, from working at my uncle's bakery and the fact that my next door neighbour owned a toy shop and they sold computers in those days, I'd bought myself a computer when I was at high school and I taught myself to program a little bit. So when I went to university, I thought, well, I sort of know how to program, so I'm not going to do computer science. But I had to do this computer science course. And during the break of the first term, I read this textbook that we had. It's probably the only textbook that I read from cover to cover while I was studying. And it started talking about some of the more technical issues around computer science. What does computation mean? And it started talking about problems that you couldn't solve on machines. And I was going, well, what do you mean there are problems you can't solve on a machine? Surely you can solve anything on a machine. So that started to get me more intrigued about the science behind computation. And I tell people, computation is the biggest unsolved problem of our lifetime. And I say that part in jest, but part seriously in the sense that computer scientists have an understanding of computation, but there are things that we haven't been able to demonstrate or to prove. And so there are gaps in our understanding of what computation is. And in fact, there's $1 million, what's called the Millennium Prize. There are 7 problems, and one of them is one of the fundamental problems in computer science, and if anyone can solve it, there's $1 million prize. So at that point I was becoming more interested in computer science. As I was doing my computer science degree, I started to become interested in reasoning and how you would represent knowledge on a machine and then reason with that knowledge. And so towards the end of my undergraduate degree, where I had to do, a thesis, not a little research project, it was around a particular way of representing knowledge and reasoning with it. And it soon became fairly clear to me that, on the one hand, I was interested maybe in human level reasoning, but humans are not good reasoners. They're not very precise reasoners. So I became more focused on what does it mean to get a machine to do the reasoning for you. I was fortunate in winning a scholarship, and I studied overseas for a year. Came back.
Whereabouts was that? Was that in Toronto?
No, that was in Milan, in Italy. My parents are Italian. I had won this scholarship here, but I went to work to study in Milan for a year, and I managed to look at some things that weren't commonly sort of researched here in Australia. So I learned some new stuff. I came back, I did my honours project, and at that point I had the choice of going back to mechanical engineering or continuing on. I applied to do a PhD, and I was awarded a scholarship, so I did my PhD, and there I focused on this area of belief change. And as I said, the main reason is because I became intrigued by how do you get a machine to... How do you represent knowledge on a machine? How do you get to then use it to reason? And reasoning is one of these problems that a machine can't solve. So we know that there won't be an algorithm that if you ask the machine a question of the knowledge that you've given it, we're certain that there'll never be a process by which it'll eventually terminate and say to you, yes, the answer to your question is yes, or the answer to your question is no.
Yep, right. That's like determining whether you're inside a for loop, early exiting.
Yeah, or whether it'll terminate, whether the loop will terminate at any point. Yeah.
Cool. Awesome. So a lot of the stuff you just mentioned there is questions I want to ask, actually. So I guess we'll be getting back to them. So the motivation behind doing this is not entirely altruistic, I'm not going to lie. The reason I pretty much wanted to set up that meetup and also this podcast was personally wanted to learn a little bit more about symbolic AI myself, because I personally believe that deep learning is getting a lot of the spotlight at the moment, but there's other approaches out there, and they should all be considered pretty much equally, I think. I think reasoning is a big one.
Yeah, I think you're right? As I tell most people, there are two basic approaches to artificial intelligence, and I think it's important that people understand that there's more than one approach. So you've got your symbolic approach, which is the approach that I take, and it uses symbols to represent objects and relationships between objects and so on. So your conceptual understanding of the world. So as I say to people, it's very similar to your algebra. Your X's and Y's, instead of standing for numbers, they stand for other objects. Yeah.
I want to drill down into that, pretty much. I think it's like the next thing coming up. So for people who are listening who might not know, symbolic AI has another name that it's known by. It's called good old-fashioned AI, which is known within the AI community. So symbolic AI was the paradigm of choice between the 1950s and 80s. Is that correct?
Yeah, pretty much. I mean, you do have non-symbolic approaches appearing in that era too, right? Probably even preceding the coining of the term AI, you've got some early work on neural networks. You've got some other results in neural networks in the middle of that time. Some good, some bad. Yeah.
But I think just like you mentioned in the talk at the meetup, I think it's going around in a circle. Last month, I think it was OpenAI. I don't know if you're aware of them. They just set up a reasoning team. So I think there you go. It's going around in a circle.
I think I told you this before, right? My guess is that in the future there'll be a lot of hybrid approaches.
Yeah, definitely.
We're seeing a lot of the non-symbolic techniques like neural networks, deep learning, providing some very impressive results at the moment, and the things they're able to do are quite impressive. So, probably from my point of view, where the issues they have are their ability to explain why they made certain choices. And that's, again, where the symbolic approaches have a little bit of an advantage in the sense that because you have a symbolic encoding of the knowledge and you can step through the inference process, you have a little bit of a hope that you can explain why particular decisions were made.
Yep. Interpretability, it's a huge one. So the question I have for you, and I'm hoping you can disentangle this a little bit, is an approach that was popular in the 70s and 80s was something which is known as expert systems. So can you, I'm just going to pretty much read off my notes here. Like, can you please elaborate what exactly an expert system is? How does it differ from a pure if-then statement? Like, how is an expert system different from that? And how does an expert system fit into the broader framework of like symbolic AI that you are familiar with? Because one of the main reasons I'm asking you this is like, this is your field. So So
expert systems were probably the early, one of the early techniques in symbolic AI that was quite popular. So just trying to sort of peel away at your sort of questions.
Sure.
What is an expert system? Well, you could just say it's a collection of rules and facts. Those rules could be just simple if-then statements. They can be a little bit more nuanced than if-then statements because they might take into account exceptions and so on. But effectively, you could probably capture most of them in terms of just simple if-then rules. The name expert system sort of tells you that the basic idea is that you sit down and you interrogate your expert and you try and figure out what sort of rules do they use to make the decisions that they make.
Right.
So it could be, a pathologist when they're looking at the test results. How do they make their how do they draw their conclusions? How do they make the inferences that they draw? Right, and it turned out that. So there's a field called knowledge acquisition, which is how do you acquire the knowledge from an expert? And you sit there and you talk to them. I don't really have much expertise in this area, but I gather that the tricky bit is really trying to get someone to articulate their expertise. And while you think it might be quite simple, it's quite difficult. So maybe an analogy would be, if I asked you to explain to me how you ride a bike, I think even though you might consider that to be something that's quite easy, once you have to sort of stop and articulate that to someone, it becomes a lot more difficult to do.
Right. Okay. Yep. I don't know if this is a question you might be able to answer, but how would you just said before that the knowledge acquisition part you're not so familiar with, but how would you translate that example of trying to ride a bike into an expert system?
I think, again, it's about the questions you ask in order to be able to elicit the information and the rules and so on.
Yep.
That's why I was saying I wasn't really that familiar with it, because I think that in itself takes a bit of expertise. How do I... What sort of questions do I ask you in order to...
Right. That's getting meta.
Yeah.
And I got a little side question here, which is what is Prolog? So I come from a Python, a little bit of R, C background. Prolog was used to encode some of these rules.
There were quite a number of purpose-built expert systems. Prolog is more a generic programming language.
Okay. Yep.
It came about by taking some of your symbolic representation techniques, so taking a logic-based approach, and essentially using the logic to express the information that you have, and then using its inference mechanism.
Right. Okay. Cool.
Now, another way to describe it might be to take a step back. So in the early days of AI, there was this notion of what's called a general purpose problem solver. So if you take your standard languages today, most of the time the computer scientists will have to provide a solution to the problem in order to tackle the problem. So the analogy I always give is just playing chess. So your standard chess playing program will just take the approach of simulating moves. It says, if I make this move and my opponent then makes that move and I make this counter move and so on, it will do an analysis of all those possibilities, and then it will say, okay, well, this is the best move to do now.
So search.
Yeah, it will just do search, right?
Yeah.
But there you've encoded how to actually solve the problem. You've written an algorithm to try and solve this problem, right? And there's some smarts there. There's all these techniques. Alpha beta pruning is a technique that tries to reduce your search space, because if you just think about chess, the number of moves and counter moves just grows quite large. So your ability to search through that space in a reasonable amount of time is limited. The general purpose problem solver, the basic idea was that you feed it the rules of the environment, in a sense, and get it to solve the problem for you. So in the chess analogy, you would just say, well, the rook moves like this, the pawn moves like this, the queen moves like this. The goal of the game is to capture the opponent's king. Go away and play the game. You don't
encode that using, like, for example, Prolog with using like logic, some form of logic syntax.
You could, yeah. Again, the tricky bit is the Prolog. What underlies Prolog is a search technique. But the point I'm trying to make here is that this type of programming is what's called declarative programming. So in declarative programming, as opposed to your more traditional procedural programming, the idea is that you represent the nature of the world, the rules essentially that you need to follow, and it will work out the solution to your problem. Prolog's one of the languages that it's a declarative programming language. So it has rules, it has facts, and you just state the rules and facts, and then it will go and try and search for a solution to your problem. The tricky bit is, again, the search space for a lot of these problems is quite large. So the nice thing about Prolog is that it gives the programmer some ability to control the search, but that requires them to know a lot more about their domain. So they need to bring in some domain-specific knowledge here.
Okay, cool. I think that's that's cool. That enlightened it for me as well. So I sort of following the structure a little bit here of the Book of Why, which is what you recommended I read. And I'm not gonna lie, I actually listened to it as an audiobook. It's probably not the best as an audiobook, so I'm going to go through and reread it again. But I'm kind of obsessed at the moment with, but we'll get to that. I'm sort of jumping the gun here. So expert systems were kind of popular up until the late 80s. And then they progressed from that to being more like Bayesian approached in the 90s. I don't know if this is, again, your field of expertise. I should have probably asked you this before. But can you sort of go into and explain to everyone why you think that happened? Why was there a transition from?
That's a good question.
Yeah.
So at this point, I'm just an undergrad at university, but my view would be that some of those expert systems did try and take into account uncertainty through some sort of probabilistic approach. The Bayesian approach is one which I think has really proved to be very effective in its ability to predict and explain behavior, right? And again, I would argue that it's a symbolic approach because you have these probabilistic variables, but it's augmented with a probability. So if you read the literature, you can view the probability in many different ways.
Yep.
One way to look at it is that it just tells you your degree of belief in something.
Right.
So
yep.
if
the belief propagation.
Belief propagations are techniques for determining your conditional probability. So often you might be. So again, it's similar to the belief change idea, right? So you have your degrees of belief in facts about your current environment, and you receive new information, and then you've got to update your beliefs on the back of the new information. Now, again, a lot of the traditional logic-based techniques don't have this degree of uncertainty in them.
Right.
And just remember that there's noise everywhere. So there's noise in, there's uncertainty in the facts that you currently believe, but there's also uncertainty in your observations and the information that you're given. And so these tries to take into account these uncertainties. And particularly in areas like robotics and so on, where the robots have sophisticated sensors, some of those sensors obviously are noisy, they're influenced by a lot of things in the environment. The Bayesian approach is one that deals with the uncertainty quite well.
Right, okay.
Yeah. So that's why it became very popular. And again, there were a lot of interesting techniques introduced to dealing with the computational issues there.
Right. Is it worth noting for people that might be listening about the link between Bayes' rule and sort of belief propagation?
Well, again, the belief propagation is just a way of calculating the conditional probability, which is what belief
belief
rule
networks
does, right? So Bayes' rule is a sort of rule, and what the belief network does for you is that it reduces the complexity of the computation.
Yep.
And it sort of revolves around us understanding that certain of the probabilistic variables are dependent on one another. They influence one another. But a lot of the variables don't influence one another. So if you took the traditional sort of probabilistic approach, if you want to update your beliefs, the amount of computation required is quite intensive. But if you understand whether variables are related or not, you can actually have a chance to reduce the computation.
Right. Yep.
So that's what that Bayesian, what's called a belief network, Bayesian network does for you. It tells you about whether variables are independent of one another or not, and then you can exploit that to reduce the computation required.
Right. So that's why it's used for sort of encoding cell phone. Is that one of the reasons?
Yeah, that's a good question. That's my guess. Again, you can use it as a bit of a heuristic.
Awesome.
Yeah. I don't know, like spam filtering was another early application.
It makes perfect sense. Yeah. Cool. I got another one here. This is again another personally motivated. So I'm going to ask this. So what is the difference between a frequentist and a Bayesian?
So like the frequentist approach is one which looks at how often something occurs.
Yep.
Right. So when you look at a probabilistic value, so something, you attach a probability of 0.9 or 90% to something, what does that mean? One approach is just to say, well, if you looked out in the outside world, this event would occur 90% of the time. So for instance, if it was cancer, what's the natural, when I say natural, well, how often does it occur? Well, if you counted the number of cases, it would give it that. The other way of looking at it is to look at it as I said, your degree of belief. So I'm 90% certain that this is the conclusion I'm going to.
How is the certainty? So just to clarify, so when you said frequency is like the number of events of a cancer in this example, is that like the number of events of cancer divided by some population or divided by the
you might just look at the general population and look at how many people have a particular form of cancer.
And that's frequentism.
Again, it's important to understand that there's a number here, and it's just the view that you give to that number. So one view could be your frequentist view, that the way you view it is that's how often it occurs. Another way to look at it is that it's your degree of belief.
Right.
It's just your interpretation of what the number means. So, the computer science are going to attach numbers to things. The statisticians are going to attach numbers to things. The difference between the frequentist and this belief approach is essentially just how you interpret the number. Is it that this is how often it occurs, or is it just a degree of belief?
Right.
And they're just different viewpoints.
Yeah, right. I feel like I've stumbled upon like quite a.
I guess it's a philosophical point. Yeah.
Okay. So was mentioning the book of why before. So in it, Judea Pearl, which is one of the, I think he's one of the founders of belief
Bayesian networks.
Networks, yeah. He sort of changed his view over time, by the sounds of things, and now he's a big promoter of causal inference. Is that something you're very familiar with? From your work?
Somewhat. I mean, his view, and this is why I sort of recommend the book to you, because he's got a very interesting take on this. And my guess is that he actually thinks causation is real in the world. As I said, it's
Right.
it's what the philosophers would call an ontological. But it's not clear. Maybe it's an epistemological construct that we use to help us reason about the world.
So can you clarify the difference between those two words?
Well,
Sorry.
We're really getting into the philosophical
that's fine,
nuances here, right?
Love it.
And the question is whether the world really operates through causation.
Yeah, right.
Or whether it's just a convenient way for us to sort of think about how the world operates,
Right, yep.
so that we can reason about, predicting things that will happen, or explaining why certain things happen. So yeah, it's a good philosophical debate. He has some very strong opinions, and yeah, again. I think for him, causality is real, and he looks at the statisticians, and I think his claim is that they gave up on causality a long time ago, and it's more about correlation than causation.
That's what I feel is the gist of the book.
And it would be good to get the statisticians' viewpoint here, right?
Love to jump in future podcast.
But again, if I look at that book too, one of the reasons I first became interested in it was just because I was curious to look at, this idea of explaining reasoning. And if you look at techniques which you might consider to be more black boxes, could you perhaps model them or approximate them using this, his causal diagram or even a Bayesian network approach, and then use that symbolic representation to be able to explain why the machine made certain decisions.
Right.
That was why I first became interested in that particular book. And as I said, that book is interesting because it's, Judea Pearl's a computer scientist, but this is a popular science book. And I thought he'd done a good job at explaining some of the issues. Yeah,
sure. Just need to have the pictures in front of you, so otherwise the causal diagram doesn't really mean
exactly
much. Moving on. So we've talked a bit about sort of symbolic AI, a little bit about Bayesian, and now causal inference. So you've also done a lot of work around computational complexity theory, which you mentioned at the start of all of this.
I haven't done myself personally work around computational complexity, but it's one of the issues that underlies knowledge representation and reasoning. And the reason is because in this field, one thing that you're interested in is how expressive the language you use to describe the knowledge. And that notion of expressivity is a formal concept, tends to be a little bit more on the mathematical side in terms of what sorts of things you're able to express. But even if you couched it in the context of a natural language like English, you might imagine that if you took a part of the language, it allows you to express certain things, but you may be limited in what you can express, particularly if you only use a small part of the language, right? In this more formal context, the tricky bit is that the formal languages that we would like to use to express knowledge have this property that the associated inference mechanism is in this undecidable class that I was mentioning to you before. And that is that if you write down all the things you know, and then someone comes along and asks a question, you know that the inference algorithm is undecidable. And that means that there's no guarantee that it will stop after a finite sequence of steps and say, the answer to your question is yes, or the answer to your question is no. So then the issue becomes, okay, well, maybe I can try and reduce the expressivity of the language. Maybe I can try and, there might be other techniques. I might just want to approximate the solution. So sometimes I'll give you the right answer. Sometimes I might give you the wrong answer. You've got to, those are where the issues come up.
Okay. So I was pretty much going to ask about the difference between P and NL space.
P and
NP? P equals NP.
Yeah.
And this is pretty much a question, taking you back to what you mentioned right at the start. There's a Millennial Prize. So can you elaborate on what the Millennial Prize is?
Well, this Millennium Prize.
And then,
Well,
yeah, why does it
there are like
exist?
there are these 7 problems in, I guess, mathematics. This one happens to be in computer science, but most of the problems are in mathematics. And there's $1 million prize for solving any of these problems, right? The one of particular interest to the computer scientists is P equal to NP. Now, again, in simple terms, computer scientists will look at a problem that needs to be solved and try and figure out, what is the computational complexity. So normally that means, in the worst case, how long might it take me to solve this particular problem? Or how much memory might it take? How much resources will this problem take to solve? If we just focus on time, the P, which stands for polynomial time,
Yep.
means that as the size of the problem increases, the amount of time it might take you to solve that problem can be expressed as a polynomial. So some sort of mathematical equation.
Right. Yep. Got you.
When you get to the next level of the hierarchy, which is NP, and it's important to understand that there's just further levels of this hierarchy, and the hierarchy keeps going up, and the problems get more and more difficult, right? Now, in NP, which stands for non-deterministic polynomial time, the basic idea is that you can check whether the solution is correct in polynomial time, but that's all you need to do. How you come up with that solution is another factor. But now it turns out that problems in that space tend to scale exponentially. So every time you add an additional resource, it doubles the time that you're going to take to solve.
Resource being?
So like typical problems in this space are, scheduling problems. So,
right.
Moving people around on your bus and train network.
So would it be
delivering parcels on
additional buses, additional?
Yeah, so additional parcels, additional trucks, additional planes, additional buses, additional people. Every one that you add can potentially double the time that it's going to take to solve this problem. So it could take you a long time.
Yep.
But as I say, it's important to understand that the hierarchy continues up. And reasoning at a very rudimentary level in what's called a propositional logic, where you just have true or false, and propositions are just like statements of fact. That's already at NP. If you were able to talk about objects and relationships between objects, then you go to this undecidable class where the machine cannot solve the problem. It's not a matter of how much time it takes and how difficult it gets as you add more resources. It's just that we know that you may never be able to solve this problem.
So that's between relations.
When the expressiveness of the language is such that you're able to talk about objects, you're able to talk about relationships between objects, properties of objects, and so on.
Through the roof.
Then it becomes undecidable.
Yeah, right.
Yeah.
That's.
But again, the hierarchy is just that problems become more and more difficult. Now, that's the way that's what the computer scientist thinks the computation looks like. The problem is we haven't been able to prove that the levels are distinct.
Right.
So while we think that there are no problems in NP that can be solved, well, P is sort of a subset of NP in a sense, right? But let's take problems that are in NP but not in P. We believe that they're in a distinct class, and that means that they cannot be solved in polynomial time. But no one's been able to categorically prove that.
Right.
And that's what the Millennium Prize is asking.
Right.
For.
Have you been keeping track of it at all? Not really.
There have been some proposed proofs, and probably proofs that P does equal NP and P doesn't equal NP.
Yeah.
But and there's a few blogs around that you can sort of follow. Okay. There's always a lot of discussion when someone comes out with a purported proof.
Yeah, awesome. Great. That pretty much covers everything I would like to talk to you about today. Is there anything you would like to mention, or? I
would encourage people to You don't need to be across all the technical detail. I enjoy the technical detail, but,
Yeah, same.
but I think it's a fascinating area. There's a lot happening. As I said, it's quite interesting how good some of the techniques are and what you're able to do with certain techniques, and our ability to explain why that's the case. I think sometimes we struggle to explain why certain things work well and don't work well. But again, then there's also the debate around the use of this sort of technology and the regulation around it. There's a little bit of discussion at the moment, but it seems to be every day there's another article in the newspaper, and there's organisations that are attempting to look at this issue of policy and regulation. And I'd encourage people to get involved in the debate and to try and get a bit of an understanding of the science that underlies it.
Yeah, same. I think the science part's key as well, actually. Cool. Thank you so much for your time today. Really appreciate it.
Thanks for having me.
Yeah, cheers, mate. Hi, everyone. So I hope you enjoyed that talk with Professor Pagnucco. I personally thought it was quite enlightening, to say the least. So yeah, if you're enjoying this podcast so far, please feel free to click or subscribe to your favorite podcast provider, as that would really help us out a ton with spreading the word with regards to all the guest the talent that's here in Australia and abroad, and stories we'd like to tell. So cheers, and see you guys next time.